Hello again, AP Physics students. In today's lesson, we're going to continue to look at these continuous charge distributions like we've been doing throughout the past few lessons. And in the past few lessons, we looked at continuous charge distributions in the shape of a straight wire, a bent wire, and also a ring. The difference in this lesson is instead of looking at the electric field at a specific point around those objects, we're going to look at what the electric potential is at a specific point around those objects. Okay, so let's start off by doing just a quick recall as to what electric potential at a point is. So the electric potential, which we're going to abbreviate with capital V, at a point P that's located from a distance r from a point charge Q is given by the following equation. And that equation is V is equal to KQ divided by R. Now, in terms of like what this means again, to have like electric potential at a point, so I can just quickly review this. The electric potential at a point is the potential difference in starting at a position that's infinitely far away and then moving across the space to where that point is. Okay, so the potential difference in starting from infinity and going to this point that's located at distance r from point Q is what we refer to as the electric potential at that point P. And we calculate it by taking Coulomb's constant, multiplying by Q, and then dividing by R. Now we want to deal with this for not just a single charge or even like a couple of charges. We want to deal with an object that has a continuous charge distribution. So the example of the object I'm going to use here is the one we dealt with in the previous lesson, and that's going to be the ring of charge. So if I want an equation for the electric potential at point P due to a differential element of charge, so you can see in the picture that I just sketched like one chunk of the ring, which the charge in that ring is dq. And I want to know what the contribution is to the electric potential at point P just from that one chunk of the charge dq. So we can take our equation up here, we can just do a slight modification to turn it into a calculus equation. And if we do that, we would get dV is equal to K dQ over R. So again, what we're doing is we're trying to identify what is the electric potential at point P due to this small little differential element of charge dQ. And we're going to call that dV, calculated by K times dQ divided by R. Now that only gives the electric potential at point B due to that single chunk of charge you see there, the one that's drawn in red, but we want to figure out the total electric potential at point P due to the entire ring. In order to do that, we're just going to integrate by putting all the different chunks of charge that make up that ring together. So if we integrate both sides, we'd have the integral of dV is equal to the integral of K dQ over R. If we integrate the left-hand side of the equation, dV, that would just become your voltage at that point, or electric potential at that point. And on the right-hand side of the equation, we can definitely pull out Coulomb's constant. So what I would have then is I would have V is equal to K multiplied by the integral of dQ divided by R. Now, there is a way to make this a little bit more simple. So if the distance r is a constant between point P and every single one of the differential elements on your continuous charge distribution, then you can also pull that out of the integral. So the distance r in this picture would be the distance from point P to where the differential element is located, and we're calling that distance r. If I picked a different differential element, it'd still be the same distance. If I pick the differential element down here, and I call that dq, and I looked at the distance from dq to point P, just try to draw a line as best I can. It's pretty horrible. Okay, that's my line R. And it's the same distance because if you go from the center of the ring to DQ, that is also the radius of the ring, which is R. So I have a right angle triangle, and it's the same as this right angle triangle up here. So I have this right angle triangle that goes from R, capital R, the radius, goes along little r here, and it goes to point Z. And that's a similar triangle to the one that I see below, the one that starts at the middle of the ring, goes to that differential element, and then back to point P, where Z is the distance from the center of the ring to where point P is. So all that means is because the distance from P to every differential element on the ring is constant, we could actually pull that out of the integral as well, which would make it even easier to solve. Okay, so let's jump straight to some example problems. Okay, so this is back to the ring of charge we were looking at in the last lesson. So I have a ring that has a radius capital R, has a positive uniform linear charge density, lambda. And it's centered on the origin, and it lies in the XY plane. Point P is located on an axis from the center of the ring. And it's along the z-axis, and it's located at a distance z, or z, from where point P is. Okay, so what I want to do is I want to A, figure out what the total charge in the ring is, and then B, figure out the electric potential at point P, and then C, I want to figure out what the magnitude of the electric field is at point P. Now, we actually did part C from the previous lesson, so I'll just write down what the result was from that lesson. And I think the equation we got back then was for the ring of charge. So we're going to calculate it just a different way here. But that equation in the previous lesson was E. So your electric field was equal to K times Z times Q, all divided by Z squared plus R squared to the power of 3/2. Okay, so we're going to get that equation in a different way. All right, so first things first, you need to figure out what the total charge of the ring is. Now, we can do that just by writing down the equation for the linear charge density. So my linear charge density is defined as lambda is equal to Q divided by L. Now, if we go here, the entire wire is bent in the shape of a ring. So the length of the wire would actually just be the circumference of this circle that you see here. So lambda would then be equal to Q divided by the circle's circumference. Okay, so Q would then be equal to lambda times C. And then the circumference is 2 pi times the radius. So this would be lambda times 2 pi times capital R is the radius. Okay, so we can go ahead and we can calculate that now. Actually, it doesn't give any numerical value, so we're just going to write down an expression for what this is. So we just have Q would then be equal to 2 pi multiplied by lambda times R. Okay, let's just box that equation. Okay, now part B wants us to figure out, okay, what's the electric potential at point P? Okay, so we're going to start off with our integral definition of this. So my integral definition would be the electric potential at that point is K, and then multiplied by the integral of dq divided by R. Now, I need to write down an equation for what R is. So if I go back to the picture, and this is the exact same way we did it last time. So we can draw a differential element here. So I'll just draw like a little differential element at this point. And again, that differential element, we can call that dq. Okay, the distance from the origin to DQ would just be the radius of the ring. So this is going to be R. And then little r is going to be the distance from point P to that differential element. So we'll just draw a line from the differential element down to point P. Okay, that's the distance R. Now, let's use different colors to kind of highlight the triangle I'm looking at in a bit more detail. Just kind of like show, like, I suppose, like the plane it's acting in. Well, it's like an angled plane. Okay, so that's my triangle. Okay, actually, I'll put the red just to show the bottom of the triangle. Okay, so there we go. Okay, and this angle down here, even though it doesn't look like it, this actually is a right angle. So it's a right angle between that line from the center of the ring to point P and that line of the radius of the circle. Okay, so we can see then that we can use Pythagorean's theorem to calculate the value of r. So if I go over here, I would have r squared. Actually, we don't need to write down r squared here. We'll go, whatever, I guess we can do it. Okay, r squared is equal to z squared plus capital R squared. And then that would be r is equal to the square root of z squared plus capital R squared. Okay, so I'm just going to take this r value and I'm just going to substitute it into the equation right here. So if I do that, I would then have v would be equal to k multiplied by the integral of dq over the square root of z squared plus r squared. Now, we can pull the denominator out of the integral because the radius of the ring is constant, and z is also a fixed position that we're trying to figure out the electric potential at. So that can get pulled out as well. So we then have v would be equal to k over the square root of z squared plus r squared, and then we're going to integrate dq. Okay, it should be pointed out here that this integral dq, let's go to a different color. We don't actually have to evaluate it, we just need to understand what it means. Which it basically just means take the ring, break it into a bunch of infinitely small chunks dq, and then add them all back together. So what this is just this is just going to represent the total charge of the ring. And the total charge of the ring is Q. And above here, we can see what that's equal to. It's 2 pi lambda times R. So I can just plug that all in up there. And then I would have, so this would then be V is equal to K over the square root of Z squared plus R squared. And then multiply by Q, which is 2 pi lambda times R. And then if we just combine everything in the top together, we get our electric potential at that point. So we could write down Vp would be 2 pi times K times lambda times capital R, and divide that all by the square root of Z squared plus R squared. Okay, and that's the solution to part B. That's my equation for the electric potential. I do want to point out that the electric potential calculations are actually really easy because electric potential is a scalar. So we don't have to worry about like X or Z or Y components in terms of like what direction the potential is. It's a scalar, so we don't care about that. which is like I said, that makes it much easier in determining in comparison to the electric field, which is a vector where we have to identify which component of the electric field is actually contributing to the net electric field. So not a concern here. Part C says, okay, we want to figure out the magnitude of the electric field, and it says specifically using the result from part B. Okay, so I want to use the equation for electric potential to figure out what the electric field is. Now, we actually have a calculus relationship between the two of them. So the calculus relationship between the two of them is, I think this is the one that's on the formula sheet. We have Ex is equal to the negative derivative of your electric potential with respect to X. Now, in our situation, our electric field is along the Z-axis, so we can just change the subscript X and the X right here to Z. So we'll just go with Ez is equal to the negative derivative of your voltage with respect to Z. Okay, so all we have to do to figure out the electric field, I shouldn't say all we have to do, because it might be a complicated derivative to figure out, is we're just going to take the derivative of that voltage function with respect to Z. Okay, so this would then look like Ez would be equal to the negative derivative with respect to Z. I'll just drop the vector sign right now. dz, and our function for electric potential was 2 pi k lambda r, all divided by the square root of z squared plus r squared. Now, before I take the derivative, pull out anything that is constant. So you can actually pull out everything, the 2, the pi, the k, the lambda, and the capital R, because the radius is constant. The only thing we can't pull out is the denominator of the equation. So if I do that, I would then have, this would be Ez would now be equal to negative 2 pi k lambda r. And then I want the derivative with respect to z of, now I'm going to rewrite this out a little bit. I'm going to rewrite this out. So the denominator you could write down, instead of writing down as a square root, you could write it down to whatever power it's to. So here, this would be z squared plus r squared to the power of 1/2. I want to write that expression in the numerator though. So to write it in the numerator, we're just going to write down the negative exponent of that. So that would then become, you'd have the derivative of, let's put it in brackets here, z squared plus r squared and raised to the negative 1/2. Okay, so I have to figure out the derivative of this. Now, to figure out the derivative of this, you have to use something called the chain rule to do it. So most of you who've done calculus already can probably very easily do this derivative. For those who have not done a whole lot of calculus, I can write out the chain rule in a bit more detail. So the chain rule tells me is that the derivative of f with respect to x is df, derivative of f with respect to u, multiplied by the derivative of u with respect to x. Now, we're not dealing with the x direction here, we're dealing with the z direction. So I'd write down the derivative of f with respect to z is equal to df du, and then multiply by du dz. Now, what I'm going to do is everything inside the brackets here, I'm going to set that equal to u. So I'm going to say Well, first of all, let's write this function down as a function of z. So we'll say that f as a function of z is z squared plus r squared to the negative 1/2. And then what I'm going to do is I'm going to take, so I'll do this in a different color here. Okay, I'm going to take all of this stuff, the z squared plus the r squared, and I'm going to let that be equal to u. So I'll say let u equal everything in the brackets, z squared plus r squared. Okay, so if I go back here to set this up, you would then have f as a function of u would be, well, u is z squared plus r squared, so f as a function of u would just be u to the power of negative 1/2. Okay, so now we've got to figure out what these derivatives are. So we're going to expand upon this equation. So this would be df dz would be equal to, okay, so the first one's the derivative of f with respect to u. So we can use the power rule to do that. So the power rule would bring the exponent down. So that becomes, let's do it in the brackets here. So we'd have negative 1/2 to the power of u. And then we subtract 1 off of the exponent. So negative 1/2 minus 1/2 would be negative 3/2. And then du dz, okay, so the derivative of u with respect to z would be just 2z. So you'd use the power rule on the z squared, bring the 2 down, subtract 1. And r squared is a constant, so you don't do anything to it. So it would just be 2 times z. Okay, so a couple things cancel here. There's 2 in the bottom. There's 2 on the top. It goes away. And we're going to replace the u here. So the u I'm going to replace with what I have u up here defined as. So it's going to be z squared plus r squared. Okay, so long story short, the derivative of this is just going to be, we'll plug it into the equation in a moment. So that derivative would be equal to, I'd be left with negative z, and then I would have z squared plus r squared to the power of negative 3/2. Okay, that's my derivative. And so I can now replace, so let's go to a different ink color. So this is the derivative I'm trying to figure out here, this whole thing. So now my electric field equation, I'm just going to replace everything in the blue box with everything in this box right here. Okay, so now we would have my electric field, Ez, would now be equal to negative 2 pi k lambda r. And then we're going to multiply this by negative z, and then z squared plus r squared, all to the power of negative 3/2. Okay, let's clean this up a little bit. So I'm just going to bring, the 2 negatives are going to cancel off, which is good. I'm also going to make the z squared plus r squared to the negative 3/2 a positive exponent again. So I'm going to bring it back down to the bottom. So that's going to turn it into Ez is equal to, it would be 2 pi k z lambda r. And then we're going to divide that by z squared plus r squared all to the power of 3 over 2. Now, let's see if that looks like the equation we derived from last time. Okay, not quite, because the equation that you see here is written in terms of the total charge of the ring instead of the linear charge density. So we'll just do a quick substitution to get the charge in there. Okay, well, here's what we know. So I can say, but Q is equal to, if you look up here, Q is 2. Oh, we should be doing it on the next slide, not here. Let's erase that. Okay, let's go to the next slide. Okay, but Q, which we got from part A, was equal to 2 pi lambda times R. So what that means is, in the place of the 2 here, the pi here, the lambda, and the R, we can replace that just with capital Q. So if I do that, it would then look like your electric field. And let's just drop the direction and just write the magnitude down. We'd have EZ would be equal to 2. Oh, not 2. We just got rid of that. We're just going to be left with KZ times Q. Okay, KZ times Q, all divided by Z squared plus R squared. So this is kind of interesting because it actually shows you, so again, that's the same equation we got from the other method. So this equation we got from the previous lesson, we had to like do all that complicated process of like setting up that integral and then like solving for the electric field. So an alternate way you can do this is if you want to figure out the electric field at a point, you can figure out the electric potential at that point first, and then just figure out the derivative of the electric potential. I don't know which way is actually faster to do, because I mean, like the method we used in the previous lesson requires quite a bit of work to set up the integral and then to actually like evaluate it. But then this one, you have to do like 2 separate steps where you have to figure out the potential first and then find the derivative of it. So either way, like you're going to have to do a bunch of work to figure out what that electric field is. But nonetheless, there's an alternate way to do it. Okay, let's go to the second example. So this is actually a continuation of the example problem we looked at in the second lesson in this advanced integration techniques unit. So we're back to this curved rod that's bent into an arc, where the arc has a radius of 0.10 meters. And we did parts A and B of this question before. So we determined the total charge of the rod previously. And from that lesson, we had a value of my charge of positive 3.1 times 10 to the negative 6 coulombs. I'm just going to write these down here because we're going to have to make use of these in a moment. And we also figured out the magnitude of the electric field at point O, and that was 2.3 times 10 to the power of 6. And the units are newtons per coulomb. Now what I want to do is I want to figure out, okay, what's the electric potential at point O? So to do that, we're going to start off by writing down our integral definition of what electric potential is. Integral definition in terms of the potential due to if you broke the arc into a bunch of differential elements and add them all together. So we'd have V is equal to K multiplied by the integral of dq over little r. So this would be K dq over. Now, every single one of the differential elements would be located a distance of the radius from the center of the ring, okay? So I can actually replace little r with capital R because the distance from point O, which is the center of that arc, to every differential element is the same, which means it's constant. You can pull it out of the integral, which is great. So you can pull it out, and then it would be k over r, and then multiply by the integral of dq. Now, once again, when you do this, all this means is take your arc of charge, break it into a bunch of differential elements dq, add them all back together, and that's the total charge on that arc. Okay, so therefore, we can just write down the electric potential would be K times capital Q divided by capital R. And let's plug this in now. So Coulomb's constant, we have 9.0 times 10 to the 9 newtons times meters squared per Coulomb squared. Multiply by capital Q. So we got that from part A when we did this example in the second lesson. So that value is positive 3.1 times 10 to the power of negative 6 coulombs. And then we're going to divide that by capital R, which is the radius of the arc, 0.10 meters. And then V, which is just a scalar quantity, don't have to worry about direction. It would be positive 2.8 times 10 to the 5 volts. Now that positive doesn't mean the electric potential is towards the right or up, because it doesn't have a direction. What the positive basically means is that if you started at infinity and you made your way all the way over to point O here, you would be working against the electric field. Okay, that's what the positive electric potential physically represents. Okay, what was that? That was that's part C. Yeah, I don't know, I wrote down A up here. I'm gonna change that. Nitpick myself. Okay, C. All right, let's go to D now. Okay, D says we're going to put a proton at point O. Okay, so proton's going to go right here. And we're going to hold it in place. So we're going to hold it in place with an applied force. So we'll say Fa. And we're going to ignore the effects of gravity for the rest of the problem. So D says determine the magnitude and direction of the force that must be applied in order to keep this proton at rest. All right, well, let's draw a free body diagram. So we're looking at a static equilibrium type problem. So we'll write down my FBD for my proton, P plus. Okay, so if I have a proton at that position, the electric field wants to make that proton move towards the right. In fact, that's the direction of the electric field at that point. It is directly towards the right. So that would, because it's a proton, there would be an electrostatic force that is exerted towards the right on the proton. Now, if I want to hold this thing in place, I'm going to have to apply an equal and opposite force in the opposite direction. So we're going to call that FA. All right, now if I look at an equation of motion, I would say, okay, let's look at the sum of the forces in the x direction. And this would be equal to 0 because this is the forces are balanced. It's not moving, there's no acceleration. Okay, so this would become Fa minus Fe equals 0. So that tells me that Fa would be equal to Fe. And then we're going to write down the electrostatic force in terms of the charge of the particle and also the electric field strength. So this is going to be Q multiplied by the electric field strength, which is E. And we determined that in part B. So we'll go back here for a moment. We got that electric field strength from part B when we solved the first part of this problem in the second lesson. So to get FA, all we have to do is plug things into the equation now. So if I plug them into the equation, I would have FA would be equal to the absolute value of your charge. This is a proton, 1.60 times 10 to the negative 19 coulombs, multiplied by the electric field that we got previously. So that's 2.3 times 10 to the 6. To the 6 newtons per coulomb. And then that's going to give me an applied force to hold this thing in place is going to be, now it does say determine the magnitude and direction of the force. Okay, so we can just add the vector sign on here and add the direction. The direction we can see from the free body diagram. So this would be 3.7 times 10 to the power of negative 13 newtons. And the direction is towards the left. So we need to oppose that electrostatic force that's towards the right. Okay, now part E says the proton's now released. So if it's released, it means we're not going to hold it in place anymore. So now FA would be equal to 0. And it says describe in words its motion for a long time after release. Okay, now obviously, if you just don't apply a force in this anymore, you just have an electrostatic force which is towards the right, which means there's going to be acceleration towards the right. So we can start off by saying that. So we'll say the proton will now the acceleration is actually going to be non-uniform. So I'm going to say it's going to non-uniformly accelerate will non-uniformly accelerate and move to the right. Now, what's going to happen is since your electrostatic force is equal to Q times the electric field. So if we go back here, what's going to happen is as this proton starts to make its way towards the right, the further you get away from the arc of charge, the weaker the electric field is going to get. So what that means is since Fe is Q times E and Fe is directly proportional to E, then your electrostatic force and your acceleration, A, are going to decrease in value the further the proton moves away from the arc. Now, what's eventually going to happen is like this proton is going to get so far away from the arc that the electric field contribution from the arc is going to be like approximately equal to 0. So what I'll say now is when the proton is very far away from the arc, your electric field is going to be about 0. And if your electric field is going to be 0, then Fe and A would be approximately equal to 0. Now, that doesn't mean that the proton is going to stop moving. It just means it's going to stop accelerating. So after it gets far away from the arc, it's just going to start moving at a constant speed. So I'll say the proton will continue moving at a constant speed. In a particular direction, so we could actually just call it a constant velocity. Okay, so that would be a thorough description of the motion. Like just simply saying the proton would go right is like pretty vague. Like yes, it will move towards the right. It'll accelerate non-uniformly with the acceleration and force decreasing the further you get away from the arc because the electric field's getting weaker. And then when you're really, really far away after a long time, the electric field would be pretty much 0, in which case there's no more acceleration. And then you just move at whatever velocity you're moving at the end of that acceleration phase. All right, so that's it for this lesson. So you can go ahead and complete the questions in assignment number 8 on electric potential due to continuous charge distributions. And then in the next lesson, we're going to look at the electric potential due to a disk of charge, which is actually something we didn't look at disks at all with the electric field continuous charge distributions. And I'll talk to you then.